Alright, yes, hello everyone. This is the recording for the mathy ciphers, I like to call them, which is the Visioneer app on Help. The date is June 23rd, 2020, and unlike usual, I actually messed up the recording during the Discord call, so this is actually just me after the fact, basically going over everything again. So if you missed it, shouldn't be too big a deal, but a lot of the stuff's already filled in. I did a lot of stuff as I went. So, first things first. We take a look at this. This is one of the things that you will find on the test. This is the part of the resource page. Sorry. This is the Visioneer table. This is the just which letters which. That is the app table, and this is the multiplicative inverse table. We will get to all of those in a second. So, first things first. The mod. So, the modular mathematics, not too difficult. So, this kind of circular model is the model that most people use. Basically just says if I go a full circle, which in this case would be to 25, which is Z, and I add another one back to A. Or if I'm at A, I go back one, I go back to Z. So the whole point is it's kind of a circle. Every single value can be changed into a number 0 to 25. And the reason why we do that is because we only have 26 letters, and there are 26 numbers in that. So that's the whole idea of the modular system in Codebusters. Yeah, so basically addition works exactly the same as it does in regular math. 1 plus 1 is still 2. But if I do something like 24 plus 23, I get 47. But 47 doesn't exist in mod, so it's basically 21. The reason why is because with modulus is basically the remainder function. So back in the day when we did remainders in like 3rd grade for math, yeah, this is literally basically that. So it's the remainder from 26. If you've done computer science, or you remember that from back in the day, that's what a mod is. So 47, the remainder of that divided by 26 is 21. And if you ever see this 3-bar thing, it just means equivalent. Because obviously 47 and 21 aren't equal, but and 21 and V isn't equal, but in this case they're equivalent. After that I kind of got lazy, so I didn't put it in, but whatever. So addition works the same. Subtraction, the same. Multiplication, the same. Division, though, is slightly different. First off, yeah, say I want to divide 5 by 7. Ignore this first off. 5 by 7 is 5 sevens, which is not a whole number. And if it's not a whole number, it can't be like in between A and B. So it has to be something. In this case, it's actually 23. So the reason why that happens is because when you divide by 7 in modular math, instead of dividing by 7, you're actually multiplying by 15, because 15 is the inverse of 7. And again, so the reason why this works is because if I basically take 5 and I add a bunch of 26s to it, and then divide by 7, because 5 plus 26 times any number of 26s is still 5 in the modular system. But when I divide it by 7, I will now get 23 instead of 5 sevens. So the whole idea is there's some mathematical proof that basically led to them realizing, oh, if I do this in modular system, instead of dividing by 7, I instead multiply by 15, or if instead of dividing by 3, I multiply by 9. So that's kind of the quick basics of the division system. You don't have to know why it works, just know that if you want to, just use the table. If you ever have to divide, just use the table. Okay? Like, nothing else is really that important. So, yeah, as long as you remember that the modular system is kind of circular, it's basically the remainder of 26, you'll be fine. So, with our calculators, sometimes we'll get numbers that are big as like in the thousands almost. So what you do is you can either, if it's negative, you can add 26 until it's positive. So let's say I had negative 10, I just add 26, I get 16. That's the number. If I have 26, the minus 26, 0. That's a number. Alright, so that's the basic way, but then you can say more advanced or whatever is, let's say I have 1,000. What I do is I take 1,000 divided by 26, and then I subtract the whole number, and then I get a little decimal, and I multiply it back by 26. And that'll give me the right number. It will be a little bit off because of rounding, but other than that, that will be the number. So, That's the main way to do it. Not very difficult. It's just kind of a different way of thinking than we're usually used to in math. So I thought I'd go over it first. Next one's a Vigenère cipher. The Vigenère cipher is very simple. It's basically addition. So you have something called the key. In this case, my key was just high. And then basically the key repeats. For hello, I just repeat it. If I can't do the whole thing, I just cut it off. But basically, I add the numbers together. So you see here, H is both 7 and 7. 7 plus 7 is 14. 14 is O. So, first things first, it's an O. Simple, right? And then E and I, E plus I, E is 4, I is 8, 4 plus 8, 12, M. L plus H, L is 11, H is 7, 18, 18 is S. And yeah, same thing with the modular thing before. If you end up getting a number above 26, you just take the mod of it. So if I had like y plus y, 20, 48, 48 minus that, yeah, and then you get what? 22. So yeah, so whatever the case, just follow, whenever you're doing any math in Codebusters, you always follow the modular system. But yeah, this is very simple. You just add them together. Sometimes it's faster, but then the other method is with this Vigenère table. So essentially how it works is, let me actually grab this. So I have my plain text L. I'm going to look at this row L. I have the key I. In this case, both I, otherwise it would be H, but I look down this row I. Oops, sorry. This row I. Find my intersection, T. Same thing with the O and the H. O, not again. O and H. It doesn't matter if I do H and O or O and H, but as long as it's done correctly, you'll see H and O. So T, V, and then TV. So that is the encoded version of this text. So, actually, let me go back. Let me just do it this way. T and V. Easy. So, the next thing, though, is the decoding. Again, it's the same thing, but I'm just going to use it. Actually, I didn't know. If I wanted to do it the math way, O minus H, 14, O is 14, H is 7, 7, so my final word is 7, so H. M and I, M is 12, I is 8, 12, I is 8, so 4, E. But now, S and H, let's do S and H for S. S 18, H is 7, so 11, so L. T and I, T is 19, I is 8, so L. So I'm just going to do that way because last letter is O, as we know, but I'll show you how to do that on the chart as well. So let's just do this M and I one turns to E first. Actually, let's just do that one because it makes our lives pretty easy. So step one. The thing with this chart you can see is that this outer rim, these outer two sides, these basically represent the plain text and the cipher text. Sorry, the plain text and the key. All the values inside would be the ciphertext. So when you're doing something like this, you see the key is H, you go across the row for H, but instead of going down for O, down O here, don't do this. Instead, look for O here and then go up. You'll find H. And sometimes, yeah, people, you get messed up like that a lot, but after you know that, just make sure you remember which direction you're going in. If you're looking for the key or the plain text, you always, remember, ciphertext is always inside. Okay, it's always one of the intersections, not actually the row and column that you go down. All right, it's pretty simple. Last one is cryptanalysis. Basically, they'll give you this. They'll give you the ciphertext and then a couple letters of plain text as a crib, it's called. So what you're supposed to do is you're supposed to use the plain text to find the key. Okay, you use this to find the key. what you do in this case, say, oh, O is H and M is E. Okay, so I basically decode that, and you can basically do the same thing as you did before. You can either subtract O and H, O minus H is 7, 7 is there, also 7, so it's H. But I'm going to show you the other way too with this chart, same concept as before. I have E, I go across E, I'm looking for where it intersects with M, so I. So, because of that, I now know that my key is HI. And yeah, this is not a perfect example because you don't know if this is the whole key, which is why they'll usually give you more letters than just 2. I just wanted to make it slightly easier here, but they'll give you more letters than 2 so you can find out the key, and they won't always be right next to each other. So in this case, I'm just gonna be like, oh, I figured out, oh, it's high, they're all just high, repeating. Then I can just do decoding to find out that the rest of the word is hello. Simple. So yeah, that's the cryptanalysis of the Visioneer. Pretty simple stuff. Next would be the affine. So with the affine, unfortunately that got cut off, but here's how it is. I'll just type it out again. So with the affine, you basically use this formula. Ciphertext equals A, which is this coefficient here, times plaintext plus B. And yeah, every time I do anything, you can put mod and mod 26 anywhere. I just leave it off because it's kind of assumed. So in this case, if I have A equals 7, B equals 4, plain text is hello. In this case, first ciphertext is equal to the value of A, which is 7, times the plain text, which is H, which is also 7, plus 4. Now, I take that, that's 49, plus 4, or 53, of course. And then, with the mod 53, you get, this isn't right, 7 times 7 plus 4, 49 plus 4 minus 26, 27 minus another 26, 1. So it's 1, which is B. And you should repeat that process for all of them. In this case, it should be B, and then 28, so 8 times 4, 30, so 6, G, I think. Let me double check. Sorry, actually no. BG, 7 times 4 plus 4, minus 26, 6, 6 is G, L and L is 11, 11, 77, 77 plus 4, divided by 26, minus 3 times 26. I get 3. So D, sorry, because obviously they're the same, both D. 14 times 7 plus 4 divided by 26 minus the whole number times 26. 24. So Y. So in this case, that is the whole thing encoded. Simple. It's really just math. One way to do it instead of the way I did it is because it doesn't change like this, like the Visioneer does. Visioneer changes because obviously you don't always know. Oh, see these two L's, someone gets added to H, one gets added to I, so you can't really make a direct conversion. But in this case, if I wanted to, I could be like, oh, every H turns into a B. Every single H turns into a B because the formula to calculate the ciphertext does not matter which letter. It only matters the value of the number. Alright? So yeah, you can do that. Next one, decoding. With decoding, the formula I like to use is the plain text is equal to, you can call it A prime. You don't have to call it A prime, but it's actually A inverse technically I think, but I don't want to type out the superscript right now. So A inverse times ciphertext plus B inverse. Now, technically the correct formula would be CT if you do the math to arrange this formula, this top formula, because this top formula is technically the one that you should be basing this off of, but I'm not doing that because I'm lazy. But it should be CT minus B divided by a equals the plain text. So yes, in any situation, you can solve for a and b using the values of a and b if they give it to you. So, but obviously, a inverse you see here is divided by a. You can't divide, so you just end up taking the multiplicative inverse, and you get essentially the same thing. So a is the inverse of a, and b prime is equal to negative b times a prime. Obviously, mod 26. But yes, so you can always solve for those in this manner. Personally, I just like to use this top one here, you see, because it makes my life somewhat easier, but it is how it is. So yeah, let's do it this way. If I have ciphertext, I'm going to do the same one again. B, BG, DDY, plain text. So I'm told with the decoding, A equals 7, B equals 4. That way I know that CT, B, so the first letter is B, 1 minus 4, negative 3. I can take the mod whenever I want to, because in the end, you're going to mod it anyway, but I don't have to, so I can just keep it as negative 3 if I want to, but I'm going to make it negative 3 into 23, okay? And then 23 times the inverse of A, which is 7, so times 15. Divide this, and then divide by 26, minus the whole number, multiply back by 26, I get 7. 7 is H. If you do that process every single time, you will end up getting the whole thing. So yeah, that's also pretty simple. Next is the cryptanalysis. The cryptanalysis is only states and national, but we'll be going over it anyway. Plain text. Again, as with Divisioneer, they will give you a set of crib text. In this case, I'll just say the first 2 letters, because you only need 2 letters. So they tell you B is H, G is E. So step 1, you can basically set up a system of equations for this, which is why I like to use this equation, because it makes it a lot simpler to use than this. So basically I set up plain text, in this case, which is H. H is 7. 7 equals A prime times ciphertext, which is B, so 1 plus B prime. Next I have E, which is 4, equals A prime times G, which is 6, plus B prime. Now, oh sorry, I left it as G instead of 6. Now, next thing to do, subtract these two formulas as you would to get rid of B prime, basically. You get 3 equals negative 5 A prime. I don't like this. Whatever. So in this case, I'm just going to change that to 5, and this one negative 3, because I can make negative 3 into 23. I get 23 equals 5 A prime. Then, instead dividing by 5, I multiply by 21, so 23 times 21, divided by 26, subtract the whole number, times 26 again, 15. So yes, A prime equals 15. Oh, sorry, A inverse. I just like saying A prime because I did the primes notation instead. But A prime equals 15, which if you look at it, A prime is the inverse of A. It is the inverse of 7. So yeah, it works. Next thing's next. Next thing, you just can solve for B prime using any one of these formulas. 15 plus, so if I do in this one, 15 minus 7, sorry, 15, so 7 minus 15, negative 8, plus 26 because it's modular math, 18, so B prime equals 18. If we do this here, B prime times A prime, mod 26 is B prime, so negative B is negative 4, times A prime, which is 15. Take the mod of that, you get 18. So yeah, it works out. Wait, did it work out? 15 negative 8. Yeah, 18 and 18. Because negative 8 is equal to 18. So yes, b prime equals 18. So yeah, I like to use this formula for cryptanalysis, but you technically should be using this one for decoding because it's the way to actually use the real values of a and b to find out what the plaintext is. So yeah, that's affine. Not overly difficult either. But next we have the Hill cipher. So the main thing of the Hill cipher is you have the matrices. Okay, so you have, in this case, my encoding matrix is the word flux. And because each letter has a number, I can assign the letter flux to be equivalent to 5, 11, 20, and 23. And following with the rest of this lesson, the plain text will be hello. So I already have this all filled out because I did it during the meeting, but we'll be going over it again. So because of the laws of multiplying matrices, this is the number of rows by columns in this first matrix multiplied by the second matrix. And for them to be able to be multiplied, these two have to be equal. And then after they're equal, if they are equal, then the number of rows in the first one and the number of columns in the second one becomes the number of rows and columns in the resultant matrix. So with encoding, you take your phrase, because it's a 2 by 2 matrix and you need a 2 by 1, you need 2 letters, you go 2 letters at a time. So first letters, H-E. See this? This one's H, this one's E. And then to multiply them together, you have 5 times 7 plus 4, 11 times 4 for the top one. And the reason why that is because this first row, first column, because this one, the way I put it is, this one contributes the number of rows. And this one contributes the number of columns. So, because of that, you go by row on this one and column on this one. And then you multiply first one in this row by the first one in this column, corresponding to the placement of this, and you move on. So first one by first one, second one by second one. Second row, you do the second row, first column instead. So first one on this one times first one on that one, second one, add them together. Eventually, if you do the math, take the mod, you get 1 and 24. And those are your first two letters of encrypted text. So B and Y. If you noticed here, I do because it's 2 by 2, I do in blocks of 2. But in this case, it's odd. There's O. What do I put here? In this case, you would put a Z. If you've read the rules, you would put a Z. It's just a placeholder. It's not actually part of the question. If you answer the question, you're not actually supposed to have the Z, I think. But basically, if you're encoding and you need another one, just make it Z. Or if you're decoding and you see an extra Z at the end, that belongs there. Alright, so that's the first thing, encoding. Second thing is so we used to be able to have questions about finding the inverse of the matrix. But they got rid of that question, but you still need to know how to invert the matrix. So, the general form is 1, you multiply this kind of edited matrix. It's not exactly that, but it's n, matrix n. This is not matrix n, by the way, but it's basically a changed version of matrix n, which we'll show you in a second, times 1 over the determinant. But of course, because we're in modular math, you can't divide. So instead, you multiply by the inverse of the determinant. In this case, and then for a 2 by 2 matrix, determinant is equal to AD minus BC. So, and then this is the arrangement of A, B, C, D, of course. So in this case, this matrix, the inverse of flux, the determinant is equal to 25, so the inverse of the determinant is also 25. Yeah, I'm sorry, it's not a great example because they are the same, so some people might get confused, but remember, use the inverse of the determinant to multiply by n. And with the 2 by 2 matrix, the matrix n is equivalent to, you basically rearrange D into this manner. So D goes here, D, you switch A and D, and you make B and C negative. You multiply it out, and then you get your inverse. Simple. All right. In this case, I'm just going to do it with you guys real quick. So opposite of D is 23. No, sorry, not opposite of D, just D is 23. Negative B, negative 11. But you can actually change negative 11 into positive 15 because modular. If you Google it, there's a couple of modular mathematics rules. Basically, it says for addition, subtraction, and multiplication, you can basically take the mod in the middle, and it still gives you the same answer. All right. So negative 20 turns into 6, and then the 23. Sorry, switch it with 5, so 5. So then you multiply this by 25 because it is the inverse of 25, and you get your inverse matrix. And then, obviously, you need to take the mod of that afterwards, so 23 times 25, 15, 15 times 25, 6 times 25, 5 times 25. So yeah, after you take the mod of that, you will get your final answer. Oh yeah, speaking of actually 25, let me go back to the affine for a second. I had this here. This is the at-bash table. Technically, the at-bash cipher is no longer included in the test. It's not actually on the rules anymore, but the at-bash cipher is an affine where A equals A equals 25 and B also equals 25. In that case, you will follow this pattern, where basically it's the alphabet flipped. Alright, so that's just a quick note. We go back to the Hill cipher. Back to 2 by 2. So, yeah, this is the inverse matrix, and then to decode something, instead of using the encoding matrix and the plain text, you just multiply the the decryption matrix by the ciphertext. Easy. Now, next thing is the 3 by 3 Hill, though. That is a lot more difficult. So, first things first, my new matrix encrypting one is approving. I've already taken this to make it, this is the number version of this, and then this, let's get rid of that first. So, it's just 3 by 3, only allowed on nationals and states. So, yeah, and encrypting, same concept, just slightly longer. As you see here, I just took hello, instead of doing 2-letter blocks, 3-letter blocks. So HEL, and then LO, and then Z in the end. Whatever. So, for example, same concept, first row, first column. First row, first column for the first row, first column box. So 0 times 7, 15 times 4, 5, 15 times 11. So it's basically just same thing as 2 by 2, except you have another multiplication. So, yeah. However, the hard part is finding the inverse of this. So this is actually written out already, but first thing you do, you take this, should move it here, you take this, okay, this is your matrix. This is how to find a determinant first, by the way, because it's still the same concept, it's still the inverse of the determinant times the kind of edited version of the matrix I like to call n. So you can either just use a formula, which is obviously a lot longer, or you can do this method, which I'm doing right now. So it's actually right there. But step 1, you basically copy the first 2 rows to the other side of the matrix. Next step, you kind of look down this diagonal. You look down this diagonal, this diagonal, and this diagonal. You multiply them together, as I did here, as I did here. Actually, let me change this to blue then real quick. Next I have, blue. No, mistake, sorry. Blue. Now, I do the other direction. This one, this one, this one, and this one. And that is this one. So, the next step is you basically subtract, you multiply by row, by diagonal for the bottom, and by the top, you subtract the bottom, no, the top, no, this one minus this one, okay? That's your determinant. In this case, I did the math. The determinant is 25, which is also unfortunate because the inverse will be 25. Now, the next step is to find the matrix n, I like to call it. So, that is next. Determinant, not overly difficult, right? So, just make sure you follow this method, and you should be able to get it right every time. However, the next thing is the finding the matrix n. So, step 1, you're going to make a 3 by 3 matrix of 2 by 2 matrices, if that makes sense. So, this is your new 3 by 3 matrix. I already have it filled out again because I already did it with the Discord call, but it is how it is. So, in this first cell, you basically find the corresponding cell in the matrix, so this one, and then you cross out. I'm going to make this back to red. I like the red a little bit more. Red. You cross out this row and this row because it has this cell in it. And now the new matrix that you put in the first one is this 2 by 2 matrix that includes everything except for the values in here. Okay? So 14, 21, 13, 6. Next one, this cell. This one, get rid of that. Get rid of this. Then 15, 17, 21, 8, 6. So you do that for every single one. And obviously you don't need to write this out once you explain it, but it's good to see how it works just by explaining it. So after that, you'll get this. You'll get this. Okay? So the next step is to find the determinant of each of these little 2 by 2 matrices with the formula AD minus BC is the determinant. So after I do that and I take the mod for all of them, I end up with this. I already did the math during the call, so I'm just going to do it. It's basically already done. Now, if you remember from before, with the 2 by 2 matrix, we had to rearrange these to get the one that I need to multiply by. Same concept here, slightly different though. So, first step, A, B, C, D, E, F, G, I. First step is this. You basically go positive, negative, positive, negative, positive, negative, positive, negative, positive. The next step is to then flip a couple of them. Wait, sorry, ignore this. So yeah, positive, negative, positive, negative, positive, negative, positive, negative, positive. Then you basically can draw this line here. These ones stay the same. Pretty sure. Let me double check. 25. Let me double check actually, sorry. No, yeah, so these ones, A, E, and I, leave them in the same place. For 2 by 2 we flip them, but in this case you don't. Yeah, A, E, and I stay in the same place. But then, between these two, and these two, and these two, flip them. So you see, D flips with B, G flips with C, and F flips with I. And then this is the arrangement that you end up with. This one right here. Okay? So that's important. Next thing to do is you take this, and you basically just insert it. Insert it in. You insert this into this, and out you get that. And then this final thing you see here is the matrix n. So the very last thing to do in order to get your matrix for inversion, you multiply it by the inverse of the determinant, which we already found, so 25. And after you multiply by 25, you'll get your inverse matrix. And using that, you can decode the 3x3 hill. So yes, it takes a long time. There's a reason why it's states and nationals only. But yeah, that's actually it. That's everything that we have for today. So thanks for listening, and goodbye. Stay safe, and yeah, that's about it. All right, goodbye.